Hello, and welcome to Office Hours. So, a couple of announcements. The Runaway Robot mini project is due on Monday. It's midnight anywhere on Earth, but ideally try to get it done over the weekend, submit it on T-Square, and done. And that way you don't have to worry about when exactly the deadline is. The week after that is Project One, which is an extension of the Runaway Robot project. It has a little wrinkle, and you might have to change your code. You might have to use a different approach, but it'll be due the Monday after that. And if you're done with all of that, you can work ahead on, 4, 5, and 6, lessons 4, 5, 6, and problem sets 4, 5, and 6. But you have a lot of time before you're ready to start that. Okay, get to questions. Let's see here. Okay, first question. Is it okay to use the code from Udacity videos with proper attribution in our source code? For example, I found that the measurement probability function is very helpful in Udacity, and I'm currently using it. So yes, you can use the code from the Udacity videos. You can even use code found elsewhere on the internet, Stack Overflow or whatever you find, as long as you cite where you got it from and document it. So we would like you to have a comment at the top of the code that says, I copied this code from, and then a URL, to Stack Overflow, you have to say, the exact page it came from. If it's a Udacity video, ideally put the URL in, but you can also say, lesson 4 part, and then you put a comment that says, this is the end of the code that I took from that source. Essentially, for this class, our particular collaboration policy in this course is that you are allowed to discuss on Piazza with other students high-level details of how you would implement something, the math, but not the actual source code. And so we're expecting you to implement in Python the algorithms and the things that you're doing. Now, obviously, if you're trying to find a formula for finding the center of a circle or something like that, you find a lot of places on the internet where here's these 3 lines of Python that just does it. And yes, you can take those 3 lines of Python as long as you cite it and just say, hey, here's where I got this from. Mostly because if we run a software similarity detection and we see, hey, wait, why are there 10 people with these exact same 10 lines of code? If they all say, hey, I got this from this Stack Exchange post, I'm like, all right, that's fine. If they're not saying that, I'm like, what's up with this? And we send to Office of Student Integrity, and bad things happen. So you are allowed to use code with attribution as long as you say, hey, this isn't mine, I got it from this other place. Keep in mind, you are allowed to do that in an educational setting from a copyright law standpoint because you are not earning money from this code, and it is educational. And so there's broad fair use exclusions to copyright for that usage. Now, if you were working for a company and actually building a product for them, using other people's copyrighted code without permission can get you and the company in big trouble. So you have to be very careful about doing that if you're actually building a product that you're selling or doing it as a job for somebody. But in an educational situation where it's a learning exercise, it's very difficult for anybody to get you for copyright infringement, even if you're using their code directly. Okay, next question. In a particle filter, let me go back. If you're reusing code from the resampling wheel, you should definitely look at post number 136 on Piazza. It's a gotcha in the example code that Sebastian has, because his code makes use of the fact that a list has aliases in it, and he essentially makes copies of his particles when he moves the particles, and so his resampling wheel code doesn't have to do that. But if you're copying just the resampling wheel code and not the movement code, that'll be a gotcha, because without copying those particles, you're going to have aliasing issues, and you'll find that maybe you're moving one particle 3 or 4 times, not meaning to. So definitely read that post number 136 if you are using an idea from the resampling wheel in the lectures. Okay, next question. In a particle filter with a small number of unique particles, what is a good method to insert new perturbed particles? How much do you perturb the particle values that remain? So if you are inserting new particles, you probably need to get rid of existing particles so that your N doesn't get too big. One thing you could do is look at your existing particles and draw a line somewhere, say 50%, and say, hey, everything better than this I'm going to keep. Everything worse than this I'm not going to keep, and I'm going to replace with something that will hopefully be better. So one thing you can do is take the 50% you're keeping and keep those 50% exactly as they are, but then generate another copy of them where each of those copies is slightly perturbed. And you're hoping that you're going to get a particle that's closer to your actual runaway robot, so that over time this new particle will generate predictions of where that robot is that's better than your current predictions by your current particles. So how should you perturb the particles? That depends on each variable. The amount you perturb could be different. You know what the noise in the system is, and so you probably shouldn't be perturbing it more than the noise. So if you have a pretty decent particle, if you move it more than the noise value, it's probably going to be worse than that pretty decent particle. If you're moving it half the noise value, it's possible it can jump to where the actual value should be. You could also do kind of a simulated annealing approach where you, over time, reduce the amount of noise you add or perturbations you do, so that your idea is that you're getting closer and closer to a good value of particles. So those are some ideas for that. Okay, we have some new questions just popping up. For the Runaway Robot project, are we allowed to submit any script other than the 4 student main files? So no. I realize it would be good coding practice if you have shared code to put the shared code in a particular script and import it from your 4 files, but let's not do that. Just do the 4 particular files that we specify, student main 1234.py, because that's what our code's going to import. And we can't be guaranteeing that we're going to be getting every file that you upload. So keep it to those 4. If you have duplicate code, so be it. It does happen. If you're worried about that, you can keep your duplicated code in one file up until you submit, and then when you submit, copy and paste it. Just be careful to test your code after you've done modifications like that to make sure it still works and what you uploaded and submitted does work correctly. So just keep it to the 4 files we request. I realize that you could, from a software engineering standpoint, they may not be ideal, but just from an ease of grading standpoint, just follow the specifications and submit just those 4 files. Okay. Question: particle or Kalman for the project? I used Kalman, but some people said particle. Which is appropriate? Which approach is the right approach, and why? Which approach is the right approach? So you've left out one option, which is a pure geometric solution. I know it can be solved purely geometrically, doing statistics on the data points and basically averaging data together and kind of narrowing down to the exact values where the robot is going. So the right approach is the approach that works the best. Now, I've seen some Kalman filters that zero in on it very quickly. Usually the particle filters take more steps to gather enough data to, converge on a solution. So personally, I think that the Kalman filter will probably give you an answer faster with less computational time. However, that being said, each individual student has to decide, am I better with the math of the Kalman filter, or do I understand particle filters and want to use kind of the randomized perturbations and kind of count on the math of the particles converging and finding a particle that's a good model. So you might try implementing both. Use one for one part, another for a different part. If you have the time to do that, implementing both systems is best because then you've learned them both. I'm not going to say there is a right solution here. I've specifically made the project part 1 a little bit easier. If you're doing a particle filter for the runaway robot, I think it would be easier to take that code and adapt it to work in project part 1. That's not to say you can't do project part 1 with a Kalman filter, but usually you're going to have to do a hybrid approach where you have 2 different state transition matrices and figure out a way to figure out which one to use for turns versus straight line segments. And so I think the migration from Runaway Robot Mini Project to Project One Polygon Robot will probably be a little bit easier if you're doing a particle filter. Not to say that your code will necessarily instantly just work. It might, but you might have to tweak it a little bit, especially some of the parameters. So from what's the minimum amount of work I'm needing to do, maybe implement a geometric solution for part 1, do a particle filter for parts 2, 3, and 4, and hopefully you'll be in a good situation where for project 1, you can use that same particle filter code and basically almost be done with it. From a learning perspective, do them both. Make them both work. So there isn't a particular right approach. My impression is that a Kalman filter could be made to work faster and with less computational expense. There is, however, the expense of coding it and how long it takes you to code the Kalman filter, and that might take you longer or it might be faster than the particle filter, depending on your math background and your experience with filters. So the right answer is there is not a particular answer that is the way to do it. In the graduate courses, we try to keep it somewhat open-ended. And so, there are multiple possible solutions. They all will work. And it kind of depends on what you're more comfortable with coding and how much time you want to put into learning the various, if both particle filters and Kalman filters. So, assuming you have infinite time, which I realize is always a constraint, doing them both would be ideal to do the most learning. But if you have something that's working, you have something that's working and you're done with the project and you can move on. Okay, I'm going to reload the questions, see if we have any others. Okay, no other questions are posted. So that's the end of office hours today. I encourage you to get your work done and submit early as opposed to panicking and doing it at the last minute when you might be making mistakes. All right, have a good night.